Self-sustained robot. Abstract. This research paper engages the reader to understand nuances of the design process of the self-sustained robot used in autonomous exploration, including link design, component selection, and active suspension algorithm which stabilizes the chassis horizontally that surpasses the compared algorithms to accomplish the desired result. On SolidWorks, static analysis was performed to track the simulated undulating surfaces for the robot to move on. Structural analysis to ensure the prototype could perform as desired. Keyword: self-sustained robot, active suspension, structural analysis, Arduino. Introduction. Self-sustained robot provides good ride quality, handling, maintains road holding ability, and supports unvarying weight. 1. To enhance ride quality and safety, many researchers have analyzed different types of suspension systems, from passive, semi-active, to active ones. The conventional suspension system is uncomplicated and well-grounded, but its performance is unsatisfactory. A semi-active system is better than a conventional suspension, but it has inadequate ability to meet high-performance demands too. The active suspension has drawn much attention in recent years because of its potential to meet tight performance requirements demanded by consumers. It can improve the ride quality and maintain good handling and road holding simultaneously. 3. Our main purpose is to develop an innovative and smart electronically controlled self-sustained system that always stabilizes the chassis to make it horizontal. The vehicle must be able to go over both smooth surfaces and sharp obstacles and should be able to detect lanes and obstacles in its path and traverse it with accuracy to reach its destination without accidents or damage to the components mounted on its chassis. 2. Link design. We began by choosing an appropriate design for the link mechanism. Some of these were noticeable after discussions. 3. Component selection. MPU 6050, Inertial Measurement Unit. MPU 6050 is an Inertial Measurement Unit, IMU, is an electronic device that measures and reports a body's velocity, orientation, and gravitational forces, using a combination of accelerometers, gyroscopes, and magnetometers. The main purpose of an IMU in our project is to get the absolute angular orientation of the chassis. This data would be fed to the microcontroller which will take action in case there is a disturbance in the orientation. We chose the IMU MPU 6050 for our purpose as it was accurate to about 0.01 degree and was cheap. B. Servo motor. Maximum payload that the robot could lift was found to be 6 kilograms, by performing a structural analysis on SolidWorks. This meant that each link had to bear a load of 1.5 kilograms, at 90 degrees the torques on the servo is maximum. i.e., 1.5 kilograms x 5.8 centimeters equals 8.7 kgcm equals 0.087 kgm. The following servo motor was bought as it satisfies our requirements and the company is reputed and verified by previous experiences. Servo name, Tower Pro MG9956. Operating speed at 6.0 v 0.11 sec/60 degree. Stall torque at 6.0 v 9.45 kgcm, equals 0.0945 kg.m. Weight 44 grams. Figure 5 servo motor. CDC geared motor. Our application, i.e. planetary exploration, requires low land speeds, 0.14 kmph for rover. For a wheel with 68 mm diameter, RPM required to attain a similar speed is 10 RPM. Motor selected, geared DC motor, 100 RPM. Specifications: 100 RPM 12V DC motors with gearbox. 125 gm weight. Rated torque, 1.2 kgcm. Load current, 0.3 A. D controller 8MG328P. An 8MG328 microcontroller was chosen for the project. The primary reasons were its abundant availability on Arduino Uno boards, experience, and ease of use. The technical specifications 7 are listed in the table, Table 1, below. 4. Active suspension algorithm. Purely kinematic-based suspension systems are not accurate enough, therefore a controlled kinematic suspension system would be perfect. 8. The suspension system must have auto-stabilization, which means it must be able to recover from all sorts of unprecedented actuations due to rough terrain. Figure 9 Flowchart of active suspension algorithm. A very important point to note here is that the two back tires have to go through the same path that the front two tires followed, and hence they just have to mimic the front two tires' actuations, but after a lag. This lag depends on how fast the robot is moving, i.e., after how long the rear wheels reach the same obstacle as the front tires did. This can be done by storing the servo actuations in an array and executing the nth array actuation for back tires. The whole process can therefore be summed up in the following flow chart, Fig 9, which depicts the flow of events inside the microcontroller. V. Simulation and analysis. A. Isometric view. From this view, one can get the clear understanding of how links are assembled and components are placed. Wheel trace, Fig 11, and chassis trace, Fig 12, indicates the movement of system going over the bumper, in which the chassis remains horizontal/parallel and reflects almost negligible error, thus achieving our purpose. Static structural analysis using SolidWorks was performed on the link to see how much deflection and how much stress is developed on the application of the different amount of forces to find out the payload carrying capacity of the link. The material for simulation is SS, stainless steel. As all our links were supposed to be laser cut, their properties are as follows. A. Modulus of elasticity equals 19,299 N/mm2. B. Density equals 8,000 kg/m3. C. Ultimate tensile stress equals 580 N/mm2. D. Yield stress equals 172 N/mm2. E. Poisson's ratio equals 0.27. The robot can therefore lift loads to 6 kg. This weight also includes the robot's weight. On actual testing of limits after prototyping, the robot could safely lift a total of 5,892 gm. Robot weight equals 1969 gm. Additional payload equals 3,923 gm. At this weight, servo motors and links had reached their limit and started to deform and twist. This result was consistent with all the simulations performed on SolidWorks. 6. Conclusion. The primary goal of designing a self-sustained robot that endures a nearly horizontal chassis regardless of terrains was accomplished. Based on the robot that we have built, it can successfully go over a smooth bump and climb a stair that is at most 5 centimeters high. The negative feedback loop gives the best results as compared to passive suspension systems, which is way more than designed. Also, the algorithm designed resulted in auto-stabilization and recovery from any angle, something which was not intended to be one of the objectives, to begin with. This system is designed for a slow-moving robot, as most space exploration robots are slow-moving in nature. The same system may not work as efficiently for a fast-moving robot. Thus it is important to note that robots with this system should ideally not be used for high-speed operations. The prototype that we have created did not have a motor driving circuit or a steering mechanism, as they were both beyond the objective of the project. It is important to not exceed the rated voltage of the various electronic devices, as it would lead to their failure, which will result in the failure of the robot. Acknowledgement. We would express our most profound and sincere gratitude to our guide, Professor Ganesh Luhar of Mechatronics Engineering, his support and continuous encouragement throughout the project. Without his guidance and persistent help, this research would not have been possible. We must acknowledge the director and faculties of the School of Mechatronics Engineering for providing fresh perspectives on the topic, which in turn helped me enhance our skills.